Welcome to Advanced Insights, where we provide just what the show name suggests. Advanced insights into some of the most exciting trends and topics in technology. On this episode, I am joined by Scott Crowder, Vice President of IBM Quantum Adoption. He co-led the creation of the commercial IBM Quantum program and is currently responsible for the adoption of IBM quantum computing by industry, academia, and commercial partners. Scott, it is so great to have you on the show. I love how our worlds have come back together. You and I had a chance really 2 decades ago to work closely together on new types of transistors and technology when I overlapped with you at IBM. And now look at where things are.
Yeah, it's been great. I actually never thought 2 decades later I'd be back, working with semiconductors as part of, my new job. But it is absolutely great to be partnering with you again, and it's very exciting.
Well, Scott, you have a job that I just think anyone that would look at is going to be jealous, because you are at the cutting edge of a new frontier of computing. I mean, everyone looks at quantum and saying, okay, there's lots of questions. When is it practical? When is it solving these tough problems? But there's no debate that it's a revolution, that this quantum revolution is upon us.
Yeah, I mean, quantum computing is an exciting revolution. It's really kind of the second big revolution around quantum. This year actually is the 100th anniversary of humans discovering the quantum mechanics as a good way to explain the universe and how the universe works. And the first big revolution actually that really transformed society is understanding that quantum is discrete or quantized. And that led to the discovery of lasers, of solid-state transistors, and the semiconductor industry, MRIs. So it really has transformed society. And we think quantum computing will be the second big revolution around how people can take advantage of quantum mechanics. And it's really about a slightly different insight. It's about the insight that if we use the math of quantum mechanics to form an information science, we can solve problems in a different way than we can using zeros and ones or binary arithmetic that we use today.
And Scott, we have a range of listeners, and some are astute in this area, but others, this is probably the first time they're really, getting a chance to hear from a quantum expert like yourself. And so maybe just a little more explanation. Like, they've all heard the phrase qubit. And, they know, we're binary in classical computing, it's 0 and 1, but here's this qubit. What does that mean, and how does that unlock quantum computing?
Sure. So the fundamental unit of a quantum computer is, like you said, a qubit, which basically holds a quantum state. And the subtlety is, unlike a bit that's either a 0 or a 1, a qubit is in a quantum state which is a superposition of 0 and 1. So if you measure it, you have some probability of measuring a 0 and some probability of measuring a 1. And that subtlety around superposition and entanglement allows you to add a couple new instructions that don't exist in classical computing, and allows you to create a whole new information science that can solve problems in a different way. And it sounds like science fiction come to life, which is why people get so excited about it. Flux capacitors, teleportation, all those kind of wonderful things. But fundamentally, we're building a computer just with that different building block than you do with classical.
And, Scott, when I think about it, and correct me if I'm wrong, but you think about the math underneath it is still fundamentally the same. I mean, there are when I mean the math underneath, I mean the math of problem solving. So there's a basis of linear algebra that we've used to great productivity in classical computing. AI takes that to the whole next step with how you leverage the multiply accumulates and can do propagation and create neural nets, and now we all benefit from generative AI and agentic AI and all that portends. In quantum computing, you take algorithms in new areas. So if you could describe how you build on the mathematics, but that quantum computers really have so much more capability, leveraging those qubits, and the fact that there are different algorithmic approaches yet to be invented here as well.
Yeah, so if you think about what kind of math that regular computers are good at, Regular computers are really good at, like you said, linear algebra, but not over huge spaces. So GPUs are really, really good at linear algebra or tensor networks. What quantum computers are really good at are linear algebra over exponential spaces, over really, really large spaces. And those are things that we don't believe classical computers, even the world's largest GPU farms, will ever be able to approach. So the reason why it can do that is, like I said before, it's using a different algorithmic approach. It's using a different information science than you can use on a classical computer. And there's lots of applications and fields, real world benefit from being able to do that kind of math, simulating chemistry, simulating multivariate optimization problems like, financial portfolio analysis and things of that nature, logistics, routing, and also things like machine learning and partial differential equations, which is really important for engineering calculations. These are like real world things that we would love to have the computation ability to solve. But regular binary arithmetic-based computers, whether they be CPUs or GPUs or FPGAs, can't approach. But this new kind of algorithms with quantum computers can.
Scott, it'd be helpful. Just share with us like an example of what classical computers just can't solve, and what yet you believe what you're working on will, shed light and shed new solutions on in the coming years.
Yeah, I think the easiest example to use is in chemistry. So classical computers can't really directly calculate large molecules because the problem is too complex for binary arithmetic to solve. So people have come up with quantum algorithms that do a better job of being able to calculate efficiently molecules. So for example, we were looking at simulating ferrous sulfide, which is a molecule that's not that big, but we cannot directly calculate that with the world's largest supercomputer, the exact calculation. But we can do a much more efficient job of calculating more accurately the ground state of that molecule using a quantum algorithm, using quantum computers.
And Scott, it holds such promise. What are the barriers? In other words, why this has taken a while, and it's an exciting time because I think those of you that are driving us forward in this space now see, I'll call it the light at the end of the tunnel here. If you could describe a little bit about what makes it so hard and about fault tolerance, because we all know, that is one of the limiters to be able to getting, a high fidelity qubits and a higher number of qubits to solve tougher and tougher problems.
Yeah, so the trick for quantum computing is that you need to calculate while it's in that quantum state. And the quantum state is, frankly, it wants to entangle with the rest of the universe. It wants to decohere, it wants to do all those things that make it hard to have good noise-free calculations. And so one of the challenges is just to build really good qubits. So that's one of the first challenges. And we've come a huge way in being able to do that. The quantum computers that we have today of hundreds of qubits are sufficient scale now that you can run quantum algorithms that are too complex to run on the world's largest supercomputers. So that's kind of where we are today. But where we want to get to is, to your point, getting large-scale fault-tolerant systems that allow you to run even much more complex problems and solve all kinds of math I was talking about before, and the real-world problems. So what do we need to do for fault tolerance? So for fault tolerance, you need to basically come up with a really efficient error-correcting code, which is more complex in a quantum computer than a classical computer. And you need to be able to basically build that in such a way that you can very effectively build a modular system. So you've got chunks that do a certain number of logical qubits, and you need to connect those chunks together so you can build larger and larger systems. Those are the big challenges that we've got in creating these large-scale fault-tolerant systems.
And you're on a journey. I mean, you're building modular systems. You're building larger and larger, quantum computers. Maybe you could, just give us a snapshot in time. Where are you, and where do what kind of pace are we on here?
Yeah, it's really exciting. If you think about it, like 9 years ago when we started this journey, I would argue there was no such thing as like a quantum programmer or quantum software or any of those things. So we've come a long way in 9 years. We now have hundreds of thousands of people who are programming on quantum computers. They're real. Today, like I mentioned, the quantum computers that we have today are powerful enough that the algorithms you can run on them, you can't run on a classical simulator. But where we need to go over the next 3 years is building out the underlying technology for these large-scale fault-tolerant systems. So in order to do that, we need to basically build a new way of connecting the qubits together that allows us to map this error-correcting code to the actual physical qubits. So there's a lot of engineering work behind that in order to build multi-level packaging, in order to be able to build those modules. Then we need to be able to put those modules together and connect them over long-range wires that are still really high quality so that you can do the quantum operations across those packaged modules. And then on top of that, we need to build really efficient decoding software, and we need to work with partners like AMD on understanding how we can accelerate that decoding software on classical computation elements so that we can effectively and efficiently build this fault-tolerant large-scale system.
Well, thank you. You mentioned the partnership. We love being a part of the quantum computers you build already with our AMD FPGAs, our adaptive compute. I know you talked about that superposition that you have to have in the qubit. And I know we're a part of that solution. And as you talk about moving forward and how classical computing can work with quantum computing, we're really excited about that and the opportunity to do more. I don't think that everyone maybe understands that idea. I know at IBM you call it quantum-centric computing, but it is indeed heterogeneous. It is CPUs. It is acceleration of using GPUs where vectorization in a classical sense is very, very effective. And it's quantum for this class of problems. So, is that now upon us, this idea of quantum-centric computing?
It is, and I think there's two separate pieces of it that are really important. So the first piece of it is that quantum computers are not going to be good at everything. They have a universal gate set. Theoretically, you could run any program there, but they're really, really slow for most things. They're only really good for the subset of things that classical computers are really bad at, like that linear algebra over exponential spaces if you really want to get geeky and into the math. So you can think about the quantum computer as being kind of the place where you run your quantum subroutine, but the rest of your program you're running on GPUs and CPUs and et cetera, et cetera, et cetera. So everything that we do in terms of the algorithms that we run with our partners to simulate chemistry, et cetera, is a combination of accelerated classical compute on leading CPU and GPUs and the quantum subroutine that they run on the quantum computer. So when we're talking about like quantum-centric supercomputing, it's that it enables you to basically solve these problems that you can't solve with just GPUs and CPUs, but you also can't solve them without CPUs and GPUs. It's the combination that allows you to solve it. The second kind of thread is in the quantum computer itself, in order to make the quantum computer do what the quantum computer needs to do, as you mentioned, we already use FPGAs in our systems to create the signals that sing to our qubits and tell them what to do. And in the future, we need to use accelerated compute in order to do those error-correcting codes I was talking about to make large-scale fault-tolerant quantum computers. So there's really two layers here. There's the layer of, to run the algorithms that we want to run and our clients want to run, the combination is necessary. And then even within the computer itself, it's a combination of the qubits plus accelerated compute together that forms the basis for these large-scale fault-tolerant systems that we're building, we're demonstrating by 2028, and we're bringing the first one to the world in 2029. So it's an exciting time. I mean, it's really, it's not an either or, it's an and.
I love that, but it is going to take education for folks to understand that. It wasn't that long ago I was explaining to folks in a CPU completely dominated world that there are CPUs and GPUs, and so I remember that explanation of how you accelerate beyond our scalar workloads that traditionally run the CPUs and how you leverage that GPU for these vectorized, parallelizable workloads. And now with quantum, there's a QPU.
Yeah, absolutely. That's exactly right. So you're adding an additional, effectively, accelerator to the mix to allow you to solve problems you can't solve today. And the one slight distinction is that you can take a program you've written for a GPU that's parallelized and deparallelize it and run it on a CPU. So you can run effectively the same algorithm on both. It's just going to be faster on a GPU. With the QPU, it's a little bit different. It's the same that it's like the subroutine that it's really good at, you run there, but you can't take the quantum algorithm and run it on a GPU. So that's the slight distinction. It's very similar to like a GPU from the mindset of think about it as like an accelerator that you're adding to the mix to approach problems that are hard to solve today. But it's a little different in the sense that once you get to like 100 qubits or so, you can't just take that algorithm and run it slower someplace else. So that makes it a little bit different.
Well, Scott, the timing of actually our chat today is perfect because we just announced recently between IBM and AMD a joint relationship. How do we partner even more deeply to bring CPUs, GPUs, and QPUs together? And I'd love to get your thoughts on the opportunity.
Yep. I think, first of all, I think there's a huge alignment of just kind of like philosophy. We didn't really talk about it yet, but like we're a major proponent of we're going to optimize the heck out of the hardware, but we need to base this on open software. Like it absolutely needs to be based on open software. And from our end, that is Qiskit is our open software development kit, for people to program on quantum computers, that acceleration that we talked about on the QPU. For IBM and AMD, I think also great alignment of, like I said before, like this is not QPUs in isolation. We need to, or our clients need to understand how the QPUs work with GPUs and CPUs in order to do the full workflow. And there's a lot of opportunity there for us to partner with AMD around their advanced technologies on the CPU and GPU and FPGA side of how you put those things together to run scientific workloads, financial workloads, et cetera, et cetera, et cetera, et cetera. And then in addition to that, AMD, I think, is going to be a great partner in us progressing towards these large-scale fault-tolerant systems that we're building, because we need to incorporate accelerated compute from vendors like AMD into our quantum computer in order to do the error correction decoding that's necessary for these large-scale fault-tolerant systems. So there's lots of opportunities for partnering here, and that's why we're so excited about it.
Well, I'll go back to your statement on open. It's obvious it's huge for us at AMD. I mean, we're open source, open ecosystem at our core. You look at our CPU compilers, all open source. Our entire ROCm stack, that's the GPU acceleration stack that we have for our Instinct GPU line, completely open. We are huge supporters of an open ecosystem. And I think about it, I go back, back to my days at IBM. I was there when IBM, which was thought of as, very much a walled garden of software, embraced Linux. And decided it basically declared very openly that open's going to win at the end of the day, and started whole new computer lines supporting Linux. Even brought Linux into the mainframes that it can run in conjunction with legacy mainframe codes. So it really is indeed an alignment as to how both IBM and AMD view the power of the community, and it's a great segue because I think, when you think about a new approach of computing like quantum, you're going to need the community with you, are you not?
Yeah, absolutely. Actually, that is kind of why I got into quantum, because back, in 2016, IBM Research put out a baby 5-qubit system on the cloud. And at the time, I was the CTO of IBM Systems, which is our infrastructure business. And what really impressed me about what they did there was that they basically said, it's more important for us to get this technology into the hands of everybody else in order for them to do research and start working on it than it is to hold it within IBM and do research ourselves and then publish it. And that's actually why I got so passionate about it. I mean, the technology itself is really, really freaking cool. But I got very passionate about it because, I fundamentally think that's the right approach. So we have spent a lot of effort on building a community in quantum around skill development, around algorithmic research, and we have put a lot of effort into it. We do thousands of people digital summer schools every summer, which is like a semester length course that we make available. We have made access to quantum computing open, free 10 minutes a month, so people can learn, how to program it. Like I said before, our stuff is based on open source software with Qiskit, because fundamentally we don't believe in lock-in. I mean, we believe that we will have the best hardware out there, and people will choose to use us, but we don't want them locked in to us just because of the software stack is completely proprietary. So absolutely 1000% agree. The community, quite frankly, we're spending a lot of money on building quantum computers. You can imagine this is not a cheap endeavor. It takes a significant amount of investment. And we want people to be able to use it when we build it. And that's really about building a community of users and a community that's driving the application research and the algorithmic discovery so that people get value out of the computers that we're building.
And Scott, how does the user community, as these real world applications start to come on in the coming years, as researchers need access now to start creating those very applications, how do we think about it? Do we think about it like cloud access today? So would these quantum computers all be in the cloud? Do you see eventually that there might be select on-premise? I know there's a lot that goes into supporting a quantum computer, but what kind of model of deployment do you see over the coming years?
Yeah, so we decided to do cloud native. So basically we actually don't sell computers. We sell a runtime environment that people send their programs to. We run it on our systems and send the results back. And I think we see that for the next 5 years as being the right model, because we've been upgrading our systems so rapidly. So instead of systems having lifetimes of 3 years, 5 years, 7 years, or something like that, we are refreshing our fleet every 18 months. And in order to do that, you really need a model where you're basically a cloud type model works. So we do have systems that are on premises also. But for those situations, we still maintain and operate them like they're part of our cloud fleet, because that makes it a lot easier for people to get started, get using it, et cetera, and it also allows us to upgrade the software continuously for the system software, and also upgrade the hardware every 2 years as opposed to every 5 years or whatever. We were basically keeping the entire fleet at the latest and greatest, or close to the latest or greatest, rather than have somebody 5 years behind, right? So that's the advantage of it. In the longer term, when people are in production, people want a stable environment, then at that point, I think, yes, the technology will likely be more traditional, long-term stable. But even there, I think there's a lot of attractiveness to this managed service kind of model that allows people to really focus on using the technology as opposed to running the technology.
Well, and I mean, just the infrastructure. I mean, to have those stable qubits, you have to operate in a very, very stable condition. You need basically cryogenic kind of temperatures, for stability. So I assume that's when you operate in that cloud model, you can absolutely assure that you've got the conditions necessary for successful cloud computing and air-tolerant computing.
We have deployed systems all around the world. So we've got systems in Germany, we've got multiple systems in Japan, we've got systems in South Korea, we've got systems in Canada, et cetera, et cetera, et cetera. So we've actually been pretty good at learning how to deploy these systems and operate them remotely, in addition to our cloud data centers. And they stay up and running for long periods of time. So it is kind of amazing how much the technology has matured from that point of view. It's not like university lab kind of situation where you got people like pouring dewars into things and like, so it is much more of like a, I'm going to say traditional data center feel to like our computation centers. You'd be surprised like how routine it's become. But absolutely, it is different. I mean, you do use cryogenics. The qubit chips are sitting at temperatures that are 1,000 times colder than outer space. I mean, it is really amazing, like the multidisciplinary stack that's required to build these computers. It has gotten to the point which I think we probably a little bit take for granted that we can deploy these systems around the world, remotely calibrate them, and all those kind of things at the same time. So we've made a lot of progress over the last 8 or 9 years on that.
Well, that leads me then to the favorite question I've been sitting on. This is where I ask you to be the seer of the future. So, it is phenomenal progress, and everyone's reading about quantum computing and the kind of hope it has to solve, industry-shaking kind of discoveries. What do you see if you just look out over the next 5 and 10 years? I mean, if you were to prognosticate, you knew this was coming. How would you prognosticate the next few years of development?
Yep. So right now we're in this weird situation. We've got computers that are powerful enough to run programs that you can't simulate on a classical computer, but not quite big enough to have an outcome that's better than a classical approximation. So next couple of years, we think that's going to change, and we're going to be able to run long enough programs that the quantum algorithm running on a quantum computer will do something better than the classical approximate method. So what does that mean? That means in the next couple of years, we think that quantum computers will have a useful impact in a couple areas, probably around chemistry, maybe around optimization. And that's like in the next 2-3 years. So not very far off. Then you get to 2029 when we're going to put a large-scale fault-tolerant system out there. That's going to unlock a lot more use cases. And that's when you're going to see quantum become more, I'm going to say mainstream is always a catchword, but mainstream because it'll be much broader application. So there's probably 2 levels. So the early adoption, around a couple use cases, probably, like I said, we think in the next 2-3 years. So 26, 27, 28. And then in 29, a big jump when you get to large-scale fault-tolerant systems. So that's not very far away. So that's like a 5-year horizon, not a 10-year horizon. And then 10-year horizon, the systems will get bigger and bigger, just like regular digital computers back in the early 50s to 60s to 70s. More and more use cases that we can't even imagine now, will get unlocked. But we have a pretty good line of sight to the technology for those first 2 steps I was talking about.
Scott, that is incredibly exciting. I have been very fortunate to have been in the industry a long time. You've had likewise a number of years, and I mean we've all seen these pivot points of change, and we're clearly upon yet another. And you're right. Everyone said, "Oh, this is 20 plus years away." And what you've really shared with us is that's not the case. It is coming upon us in the next 5 years to really attack the kind of problems we just couldn't solve before. Super exciting. And I just want to say thank you very much for joining us on the show here. We're thrilled at AMD to be partnering with IBM and helping create an open ecosystem around quantum-centric computing.
Likewise, we're very excited about the partnership, and we're excited what quantum computing is going to bring. I mean, if you look at where we are, we're going to hit quantum advantage in 2026. We're going to have fault-tolerant quantum computers in 2029. And partnering with people who are bringing the classical expertise to that is going to be critical to both of those landmarks. And we are very excited about what our users can do in the next couple years around chemistry, around optimization in multiple industries. And we can't even imagine what we're going to be able to do at the end of this decade and the beginning of the next decade.
Thank you so much, Scott. There is simply going to be no lack of excitement and advancements in our world of computing. I truly enjoyed chatting with Scott. If you think about the main takeaways, for me, you read about everyone saying quantum is 10, even 20 years away. And he really shared with us a vision of how we're on a real upswing of quantum being able to solve real-world problems, starting with the releases in the next 1 and 2 years, and yet that there'll be a constant cadence of enhancements to where in 5 years we're going to be amazed at some of the discoveries and problem solving coming out of this quantum-centric world where classical computing, CPUs and GPUs, work seamlessly in an open ecosystem with QPUs, quantum accelerated computing. It's going to be an incredibly exciting future for computation. Thank you for joining us today on Advanced Insights. I look forward to bringing you more in-depth conversations on cutting-edge technology, industry insights, and visionary perspectives from some of the brightest minds in the field. You can watch the video show on AMD's YouTube channel, or you can listen on audio-only platforms including Spotify, Amazon Music, and YouTube Music. Technology is always advancing, and I can't wait to share more insights with you next time.